If you force a sprawling, dense desktop portal directly into a vertical smartphone screen, the user interface fractures. The GSB portal system serves thousands of concurrent academic users. Those users are divided across 6 highly distinct roles, each requiring their own specialized data views and interaction models. Mobile architecture functions as a targeted companion, isolating specific high-value workflows from the broader desktop ecosystem. We can map the specific engineering constraints of this companion architecture by looking at the GSB mobile app. The system rests on 3 pillars. First, a ruthless feature sieve that dictates exactly what data makes it to the device. Second, a frictionless authentication loop that balances heavy academic data security with immediate access. And third, a centralized, database-driven pipeline for asynchronous alerts. The design must resolve the competing demands of these 3 vectors to avoid the fragmentation and security lapses common in enterprise porting. The first step in preventing interface bloat is applying the 2-tap rule. If an enterprise workflow takes more than 2 taps to explain, it is explicitly excluded from the mobile build. Operations that pass this filter are red-heavy or alert-heavy. Students pulling their current semester grades, staff sending a chat message, or professors executing a single-tap approval. Entire user portals are explicitly blocked from the mobile architecture. The administrative dash and timetable suites remain web-only. Workflows like calculating timetable conflict matrices or executing machine learning assignments require wide data tables. They naturally bounce off the 2-tap boundary. By enforcing this boundary at the product level, the interface remains confined to immediate, high-frequency actions that fit a vertical screen. Engineering resources are then freed from building complex multi-screen forms. The entire development effort pivots to optimizing mobile native strengths, aggressive local caching, and real-time push delivery. You cannot achieve high performance at the application level until you subtract the workflows that don't belong there. The app handles sensitive academic and financial records protected by system-level secure flags. Yet the required user experience is continuous access. Users expect the app to open instantly, without a login screen, every time. The backend issues 2 distinct keys, an access token that expires in 30 minutes and a refresh token that lives for 60 days. During a cold start, the app intercepts the launch, pulling tokens from the hardware-backed secure store. The access token is usually expired. Before the UI renders, the client fires a silent authentication request using the valid refresh token. Once the server validates the session and returns fresh keys, a local security gate triggers. The user clears a biometric check to unlock the interface. On the back end, replay attacks are neutralized through rigid token rotation. The database tracks every refresh token via a unique JTI. With every silent refresh, the server issues a new JTI, flagging the old token as replaced. If a user logs out, the server explicitly revokes that active JTI with a timestamp. Because the database checks this exact ID on every request, a stolen token is rejected the moment it is presented, regardless of its expiration window. To protect the tokens while they travel, the app implements Leaf SPKI certificate pinning. It verifies the exact cryptographic signature of the server, dropping the connection immediately if a man-in-the-middle proxy is detected. If the hardware biometric sensor fails or returns an unexpected error, the local gate fails secure, locking the user out entirely until they can re-authenticate. Frictionless access requires a heavier security architecture. The burden of authentication is moved away from the user typing a password and onto an automated, hardware-verified token rotation. Students frequently navigate concrete campus buildings where cellular signals drop. They still need immediate access to their daily schedules and recent grades. The app enforces a strict 30-second network timeout. If the server doesn't respond, the UI automatically falls back to an offline state. To populate that state, data from the TANstack query layer is aggressively cached down to the local device storage, configured with a 7-day time to live. Writing API responses directly to local storage creates a severe vulnerability. Auth payloads, user profiles, and session keys would sit on the device in plain text, easily extracted from an unencrypted backup. The architecture relies on a strict query dehydration filter. Academic data, like schedules, pass through the gate to disk. Any response containing authentication or profile data is explicitly dropped. It lives only in active memory and dies when closed. When the network drops, the interface renders a persistent offline banner. reading only the academic JSON payloads that survived the filter. Offline availability works, but if it compromises the device's data at rest posture, the implementation is flawed. Selective data dehydration solves the engineering requirement without exposing the user. Companion apps are rarely opened proactively. System engagement relies entirely on highly targeted push notifications. The standard approach is to paste delivery scripts and Firebase credentials directly into dozens of individual API controllers. The code to fire a push notification sits right next to the code that approves a grade. The GSB backend centralizes this. API controllers execute their specific business logic and simply insert a generic notification record into the database. Attached directly to the notification model is an event listener. When a new row commits, this listener fires the outgoing push payload. The third-party delivery execution is completely abstracted. The API endpoint handles the core data update, unaware of the notification mechanics firing downstream. But an automated pipeline scales poorly if a single workflow triggers multiple system updates, bombarding the user's phone with duplicate alerts. To fix this, a second database listener is installed, a pre-insert hook dedicated entirely to global deduplication. Before any record is written, the listener checks if an identical notification type was sent to that specific user within the last 24 hours. If it finds a match, it attaches a silent flag to the incoming object, instructing the delivery pipeline to stand down. The row still inserts into the database to preserve a complete historical audit trail, but the actual device ping is suppressed. Tying the delivery mechanics directly to the database layer guarantees that every alert is sent and the deduplication rules are enforced across the entire enterprise backend. This technology combination, the React Native client, strict storage boundaries, and Python backend, creates a highly specific pipeline. The offline filter achieves zero plaintext tokens on the device. Native ORM hooks guarantee push delivery, driven entirely by database commits. Relying on hardware-backed storage for token rotation and isolating workflows that require heavy interactions allows a small engineering team to confidently secure thousands of user sessions. Enterprise mobile tools find their utility in the elegant management of offline states, authentication friction, and the precision of asynchronous alerts.